I'm John.
I'm awesome.
And I'm Steve.
We are proposing an add-on module for existing shopping carts that automatically returns them to the shopping center without requiring the shopper to manually return them themselves.
As everyone knows, customers don't always return the shopping carts to the building after they're done shopping, or even the parking stalls that are set in the parking lot. This is expensive, as shopping centers have to pay employees to collect carts, and also dangerous, as shopping carts left in parking lots cause over $1 million in damage every year. The motivation behind this project was to create a safe, cost-effective device that eliminates these problems. Our market research consisted of an interview with Sarah, a manager at the Home Depot at the Chesterfield Valley Shopping Center. Her main concern was the durability of the device. Shopping carts last an average of 5 years, so our device had to be able to match that lifespan in order to be feasible. Her other concern was that the elderly often use shopping carts to support themselves, so a cart that gets away from the shopper at the push of a button and leaves them stranded could be a liability to the store.
Our primary performance goal was also given to us from our market research interview. A shopping cart that is unable to stack with other shopping carts is useless to a store because they are unable to store it with how much space it takes. So every step of our design process took into account what space in the shopping cart would affect the stacking ability. As you can see from the picture, the rear wheels and the rear part of the tray do not affect whether a shopping cart can stack or not, so those areas were the primary focus of our design. Another performance goal we needed to consider was safety. Shoppers often leave their young children in the basket while they shop. We need to ensure that the shopping cart would not automatically return to the stall while the child was still in the seat. To accomplish this, we placed a pressure sensor on the seat, where if it detected enough weight, the motors would not start. The final performance goal that we needed to address was automation. The shopping cart needs to be able to return itself to the stall, otherwise it won't address the concerns that we wanted to.
Navigating back to the store is complicated due to the dynamic variables of the parking lot, such as moving vehicles and walking customers. To make sure the cart returns to the store safely and reliably, we decided to have the cart follow a preset path in the parking lot. The path would initially be painted parallel to the parking aisles and then turn 90 degrees towards the return door of the store. To achieve this, the cart has reflectivity sensors mounted beneath the carriage that tells the onboard computer if the cart is on the line. If the cart veers off the line, the computer will pass more power to one wheel, leading the cart back onto the line. The cart is equipped with distance sensors, infrared sensors, to determine if there's anything in the path of the cart. If there is, it'll stop.
All in all, the cart was produced for $304 out of an estimated budget of $380. However, we believe that by buying things in bulk and using appropriately powered motors, the cost of the mechanism will be reduced to under $100. We will note that some parts of this cart were taken from another robot. However, because the motors were so powerful, we still expect the project to come in under budget. There are several upgrades that will be made to the final product. First of all, the cart needs to be water resistant as it operates outdoors. This will be done by encasing the back of the shopping cart and also the chains, which will be a safety bonus. One of the biggest weaknesses of the cart was the rubber clamp that mounted the motor to the shopping cart. The rubber inserts on the clamp rotated, which allowed the motor to become out of plane with the sprocket.
To eliminate the chances of part failure, a static stress analysis was performed on the aluminum drive shaft using SolidWorks software. The maximum torque applied to the shaft during regular use was calculated using a free body diagram. The analysis found that the maximum stress obtained by the shaft in regular use was an entire order of magnitude below the failure stress, so this ensured that the part would not fail. However, when the part was actually made, threading used to put in a set screw and other factors led to the failure of the aluminum shaft. Despite the results of the study, we decided to use a steel drive shaft instead of an aluminum one.
Once the Arduino is already in the cart, the applications for this mechanism are endless. A common frustration in American society is waiting in lines at the supermarket. But if you could check out in your cart, there would be no more lines. Your cart is the cashier and the checkout. This will be done by mounting a credit card reader to the cart. A pressure sensor in the carriage can also weigh fruits and vegetables and let the shopper know if an item has been placed in the cart that doesn't belong there. The implication of these smart carts is that a store is always at 100% checkout capacity. There will be no more lines at holidays or any other busy time of the year because the store can always accommodate everyone who wants to shop there. Thanks for listening.